Hello, this is a quick errata video. After I posted the second lecture, Ahmed pointed out that there was an error in the proof of the last claim. Okay, the error is at this point where actually a very simple how do you say very careless lapse of getting the signs of a expression wrong and hence the inequality wrong. Okay, so at some point I have this expression here, right? Let me use another color. I have this expression here, and then I use the fact that A is the smallest norm vector in the set D and Z is another vector there. So the norm of Z is lower bounded by norm of A. I substitute it here, but then that's not correct because I am having a negative sign here, right? So for a negative Z, negative norm of Z squared, this negative norm of A squared only serves as an upper bound. Okay, but we are now working in the opposite inequality case, right? So this step is wrong. Okay, and this is what Ahmed had pointed out, right? So I cannot do this substitution like this. So how do we salvage the proof? Okay, so we will maybe since we will have to do this proof once more, right? Maybe I'll write it in a fresh page. Okay, that is better. So what is the claim that we are trying to prove? Okay, the claim that we are trying to prove is that if A is the smallest vector in a convex set D, then for all vectors set in D we have inner product of Z comma A larger than or equal to norm of A. Okay, so this is what we were attempting to prove, right? So maybe we will first show a slightly weaker claim that it is lower bounded by norm of A squared by 2. Okay, and then we will kind of remark as to how to extend this proof, right? So this is your set D. By the way, we should also say, if A is if D contains the 0 vector, then A is also the 0 vector because that has the smallest norm, and then this is kind of this inner product of Z with A is 0, and we are just saying that 0 greater than or equal to 0. There is nothing interesting here. So the interesting case is when the origin is outside of the set D and your A is in some sense the smallest vector in D and your Z is somewhere else. Okay, and what we want to show is that whichever be the Z, this inequality will hold. Okay, so in the last class what we did is that we kind of analyzed the vector which was at the midpoint of A and Z, which was like half of A plus half of Z, and that is what gave us the wrong proof. Today, to correct it, we will kind of analyze a vector which is something like somewhere which is closer to A. So let's call this. So let us call this in between vector as some Z prime. And what is Z prime? Z prime is some alpha times Z plus 1 minus alpha times A for some alpha in, let's say, open interval 0 1. Okay, so I want somebody who is strictly between A and Z, not A or Z, right? So by convexity we know that this is also in D by convexity of D. We will fix the alpha later, right, when we reach the particular step in the proof. Okay, so as of now alpha can be any number between 0 and 1, and what we know is that your A is the smallest norm vector, so the norm of A is less than or equal to norm of Z prime, because Z prime is also a vector in D and A is the smallest vector in D. I square both sides to make my analysis simpler, and norm of z is nothing but norm of alpha z plus 1 minus alpha a, the whole square, right? And this will turn out to be alpha squared norm of z squared plus 1 minus alpha the whole squared norm of a squared plus 2 alpha 1 minus alpha times the guy whom we actually want, z comma a. So now if I rearrange, what I'll get is z comma a is lower bounded by this norm of a squared minus 1 minus alpha the whole squared norm of a squared minus alpha squared z squared by alpha 2 alpha into 1 minus alpha, correct? I am just rearranging the terms after taking them to the other side. Okay, so now you have an alpha squared common norm of a squared common here, and it is 1 minus 1 minus alpha the whole squared. So you can verify that that will be actually 2 alpha minus alpha squared, right? Because 1 minus alpha the whole squared is 1 minus 2 alpha plus alpha squared. There is a minus here, and that 1 cancels out. Norm of a the whole squared minus alpha squared norm of 2 alpha into 1 minus alpha. Now you see, if I assume that alpha is not equal to 0, which I already have, because alpha, that's why I said alpha is in the open interval 0, 1. So since alpha is not equal to 0, I can cancel out an alpha, and I'll get 2 minus alpha times norm of a the whole squared minus alpha times norm of z the whole squared by 2 alpha into 1 minus alpha, right? This is what I want. Now what I want to do next is I want to actually lower bound this whole thing with 2 minus alpha. This is where somehow I made a mistake last time. Two alpha into 1 minus alpha. This is what I want. But if I want this, then what am I saying? I am saying that I am lower bounding minus alpha z squared by norm of alpha square, or right, this alpha z squared I am upper bounding by a squared, right? And so yeah, your z may be very large, norm of z may be very large, but if I choose alpha small enough, I can still achieve this, right? Alpha can in fact be any number in the interval 0, 1. I cannot use 0 because then this cancellation is wrong. Okay, by the way, when I did this calculation, there is no more 2 alpha here, there is only 2 here, right? It's only 2 times 1 minus alpha. Yeah, so I cannot use alpha equal to 0, but other than that I can use alpha as small as I want, right? So I will use an alpha which is smaller than norm of a squared by norm of z squared. Okay, remember that any norm of a is already less than or equal to norm of z, so this is less than or equal to 1, alpha will be less than or equal to 1, right? In this case, this inequality is correct. So what do I get? So there is a 2 minus 1, so this is 1 minus alpha times norm of a square, norm of a squared by 2 into 1 minus alpha, or which is equal to norm of a squared by 2. This is what I had promised, right? Norm of a squared by 2. But now if you see, I mean, if I kind of play with this, which I won't get into the details, if I play with this, like, instead of this, I can actually choose an alpha to be, maybe half of this. Let me use another color and then just say, right? If I can actually choose alpha to be something like, half of this a squared by z squared, then what would be my minus alpha z squared, you will be able to lower bound it by norm of a squared by 2, right? So if you do that, then instead of a squared here, you will get half a squared, and here instead of 1 you will get something like 1.5 minus alpha. So this numerator keeps growing, right? So if you want, you can kind of, instead of this norm of a squared by 2, you can go upper and almost you can like if you make, instead of this half, if you take a 0.00001, then you will almost get close enough to your a square. Okay, but anyway, we won't need such a such a tight bound there. So this is enough for the proof. Okay. By the way, before closing this video, maybe I'll also remark as to what is happening here in a geometric sense, right? So let's say this is your a vector, which is the smallest vector in a convex set, right? And if you have a z again in your convex set, this is a 90 degree. If you have a z somewhere again which is also in your convex set, the z vector, such that okay, let me also, before trying to give that intuition, what we are saying is that z inner product A is more than or equal to norm of a squared. Another way to write this is z A by norm A greater than or equal to norm A, right? Now what is this? This is the projection of z along A, right? To get a projection of a vector along another vector, you take the inner product with the unit vector along that direction. A by norm A is the unit vector along the direction of A. So this is the projection of z along A, and we are just saying that it is larger than the length of A. Okay, that's all that we are trying to prove. Now how will we prove? Suppose not. Suppose this was not true, then that means there exists a vector z in D, A is also in D, D is a convex set, such that the projection of z along A, okay, so that's why I have drawn a perpendicular here to A. This is the projection of z, right? This is your z of A by norm A, okay? That is smaller than the length of A itself, right? Then what happens? Okay, I mean, just to make it a bit more legible, yeah, this is your A, right? Then what we are saying is that in this case, A is surely not the smallest vector in D, because since A is in D and Z is in D, this entire set of points, in the line segment which connects A to Z is also in D. And now, since this is a 90 degree triangle, this and this are actually acute angles, right? So 90 degrees, so these are acute angles, and hence if you actually draw a perpendicular from the red line to the origin, right, that would actually be somewhere here. Okay, so geometrically, and then this point z prime is actually, or A prime, let's say, is in D. A prime is also in D because it's in the line segment joining A and Z, and it is of length smaller than that of A, which violates the choice of A. It contradicts the choice of A, because A was supposed to be the smallest guy, not A prime, right? So this is the geometric intuition behind this argument. But yeah, the calculus way of doing it is this. Okay, so once again, thanks Ahmed for pointing out this mistake. Okay, bye.